In these videos, we're going to look at a set of problems that are related to robot motion planning. We're going to look at only a simple version of these type of problems. So we consider a problem in which we have a bunch of obstacles, P1 up to Pk, where each obstacle is polygonal. In other words, it's made of straight lines. These obstacles we assume that are inside a scene that's like a bigger obstacle that surrounds them. And we also have a robot, which is also represented by another polygon. And we would like to find if it's possible for the robot to travel from, let's say, in a starting position to an end position without essentially going through the obstacles. In other words, we obviously assume that the robot cannot go through the obstacles. But to simplify things, we only considered that the robot can only move by translation. In other words, it cannot rotate. So to see why this simplifies the problem is that if you don't have rotations, if your robot can only translate, then you can have a reference point for the robot. In other words, you can represent the location of a robot at all times with a one point P. So to do that, you fix, let's say, a center of a robot. So let's say you pick a point that represents the center of the robot. And now if you have the location of the center of the robot, then the location of the robot is uniquely determined. Note that this is not the case if the robot can rotate, right? Because you could have the robot that is centered at the same position or same point, but it could be rotated a little bit. By disallowing rotations, we're actually reducing the total number of free parameters that we have, or the free variables that we have to 2. We only need to specify the location of the center of the robot by 2 coordinates, x and the y. If you have rotation, then we essentially have a 3-dimensional problem, because in addition to location, we also have a rotational angle. And this is just for 2D. For 3D, if you have a 3-dimensional robot, you need 3 coordinates for the location and 2 coordinates for the rotation. So as you add more dimensions, this problem gets more complicated. So here we're just looking at the most simple version of the problem, which is without rotations. Yeah. So yeah, I'll talk about this. Okay, so how do we do these type of solutions, or how do we solve these type of problems? The main idea is to define the notion of a parametric space and also the forbidden space. So remember that in this version of the problem, the location of the robot, or the position of the robot, can be represented by its location of its center. So therefore, we could say that some of the locations are forbidden, like the robot cannot be inside the obstacle. So therefore, the robot should be placed in such a way that it does not penetrate any of the obstacles. So that limits where we can place the center of the robot, or the point P. So therefore, it seems that intuitively that if we could somehow enlarge the obstacles such that the only points that are left as like empty spaces are the locations that are valid, then we just simply need to solve the connectivity problem. Can we start from a valid location and go through and reach a valid target location only through this valid space? So there are 2 main problems for dealing with this. One is that how do we enlarge the obstacles? What is exactly, how do we do that mathematically? And finally, once we have enlarged the obstacles, how do we actually solve the problem of reachability? And we're going to tackle these problems in the next videos.